Okay, fine. So let me begin. As Professor Tripathi underlined, the importance of explanation can never be undermined. And right from the beginning of any kind of intellectual pursuit, human beings have been interested in reducing observations to a small number of rules and regularities by which a large set of phenomena can be explained. For example, every action has equal and opposite reaction is a crystallization of many different phenomena where this rule of nature applies. Every action has equal and opposite reaction. Though what is left out there, which also is critical, is that action and reaction work on different bodies. So explanation needs to be accurate. Explanation needs to be complete also. Now in this talk, the title is Explainability and Cognition. As we go forward, we'll see the role of timeliness of the topic again cannot be undermined. The age of deep learning has arrived, and umpteen number of problems are being solved using deep learning systems. But these systems have remained extremely inscrutable. We most of the time do not understand what is going on. So the research on explainability started in the context of machine learning driven AI. However, as I mentioned, the notion of explanation is much, much older. This is as old as cognition and any kind of intellectual activity. Now, the roadmap that is before you for the next 1 hour or so is we'll dwell a bit on explainability background, the terminology associated with explainability, the intimate connection between logic and explainability, which interestingly has still remained beyond the current research, which is on correlation capture. Causality is not yet captured, and I see intense activity, including our own research group, investigating this notion of causality, which actually is explainability. We'll also look into popular techniques for explaining the machine learning models like LIME, LRP, IG, which are three predominant uh, techniques for explainability. We'd like to cover these three. And interestingly, explanation helps designing techniques for decision making, classification, clustering. And our work on cognition-based explanation, which helps natural language processing solutions, is also something I would like to touch upon. So this 1 hour, I have divided into these 4 segments as far as the presentation goes. Do feel free to ask any questions or make any comments. I believe the participants are unmuted by the organizers. So if you have to say anything, please raise your hand or raise the question on the chat box. Now, closely related terms, the terms which associate with explanation, come from two different themes, as I can tell. One is logic and philosophy, which is very old, and the notion of axioms, self-evident truths, inference, reasoning, correlation, coincidence, causality. These are terms which are as old as human intellectual activity, once again. Now, it is the axioms which are very interesting. Axioms are self-evident statements. Now, self-evident, of course, has an element of subjectivity associated with it. Self-evident to whom? However, the general understanding is axioms are and so simple to grasp that their truth doesn't require any more support, any more background support. And they're very simple most of the times. But axioms by themselves are not uh, very interesting. What we can do with axioms is that we can draw inferences by using concrete inferencing rules. This process is called reasoning. Most of the time, the reasoning arrives at the axiom itself, after which no more question is asked. But interestingly, we also find that explanation, the need for explanation gets triggered by observing correlations. So for example, Professor Tripathi mentioned aroma, the sense of smell, into which not much investigation has been done. But we know that COVID-19 has made the sense of smell and taste come to our conscious observation. We know that COVID-19 often is associated with loss of smell. Now, this is a correlation. A COVID-19 occurrence of COVID-19 and occurrence of loss of smell are going together. Okay, these two phenomena occur together. There's a correlation, a need for understanding why there is loss of smell. Okay, so that is a deeper investigation, and we transit from correlation to causality. But as going forward, we'll see that machine learning explanation is still predominantly correlation based. So coming to the AI ML paradigm, which relates to explainability, there are important terms like trustworthiness. Again, we are concerned with some areas of AI where trustworthiness is critical. Healthcare, judicial system, where we need to have trust on the decisions made by the AI system. We also need fairness. There is deep research on how to make the data bias-free. Is it that a particular gender is disfavored when it comes to a choice, when it comes to an opportunity? A machine learning model can do that. We'll see a few examples. The question of ethics, interpretability, transparency, the notion of outlier, anomaly, all these are very related terms, very closely related terms with explainability. Now, before going forward, let us just remember once again, this is for the purpose of deeper and more serious research, that while logic and philosophy have concerned themselves with the notion of causality, AI and ML has predominantly been, uh, for absence of better terms, obsessed with capturing correlation. Not to say correlation is bad, not to say capturing of correlation is undesirable, because that is what triggers investigation into causality. But we should take note of this limitation in AI/ML's investigation into explainability. However, it is important to delve into those techniques. Now, we need to understand the definition of explanation. English WordNet defines explanation as a statement that makes something comprehensible by describing the relevant structure or operation or circumstances. And indeed, that keyword structure, operation, and circumstances have led to three different paradigms of explainability. The Oxford Learner Dictionary describes explanation as a statement, fact, or situation that tells you why something happened, a reason given for something. And Longman Dictionary describes explanation as reasons you give for why something happened or why you did something. So all these definitions are quite related, as you can see. However, we will focus on structure, operation, and circumstance in the context of explanation. Now, these are three different kinds of explanation. So, structure-based explanation insists that we keep reducing to simpler and simpler statements until we hit a self-evident fact. So to take an example, something happened due to flight delay. Flight delay happened due to airport congestion. Congestion happened due to election rallies. Election rallies happened due to the need for attracting votes. Attracting votes happened due to the desire for winning election. I mean, one can go on this long regression path asking as to why something happened. And it is our choice to stop at a point either because it is self-evident or because we have resource constraint. We do not have resources to question further. This is structure-based explanation, and we note that this amounts to progressive reduction of the situation into simpler and simpler elements. Operation-based explanation describes how something happened. Okay, so how did you fix the deep fridge? I switched off the power, let the ice melt, and switched the power back on. So this is also a kind of explanation, and there the keyword is how. And circumstance-based explanation mainly describes why, what circumstances led to current circumstance. The circumstance-based explanation has some overlap with the structure-based explanation because in both cases, we ask why. However, in circumstance-based explanation, the focus is on situations, okay, uh, in preference to other factors constituting that situation. So COVID-19 resurgence is the circumstance of interest. And why this resurgence happened? This happened due to opening of facilities and due to casual behavior by people. And interestingly, while structure-based explanation has a rigorous line of uh, nodes forming a chain, uh, the circumstance-based explanation is not necessarily a chain always, and many factors come together to create a situation which can be parallel and independent. Now, to take note of explainability and logic, we look at one of the pillars of reasoning, which is predicate calculus, and one of the most important modules in artificial intelligence. Now, elements which are provided for explanation are axioms and inference rules. Um, if we look at the formal structure of propositional logic, predicate logic, and so on, we see that these systems are extremely rule governed, and there is strict description of structure and rule application. The constituents of formal systems are symbols, which are variables, well-formed formulae. This pertains to the syntax of formula. There are very strict rules as to how formulae can be constructed. There are inference rules by which new formulae are obtained. Semantics is assigned to the variables and the expressions. There is a very rigorous notion of proof and soundness, completeness, and consistency, along with decidability, the last mentioned being a computational concern, whereas soundness, completeness, and consistency are logic concerns, they form something called a formal system. So many of us have used Boolean algebra, propositional calculus, without really uh, taking note of the fact that there is a very well laid out and rigorous framework for carrying out operations in that system. Okay, such a system is called a formal system. Our hands are really tied by means of rules. Now, propositional calculus has been formalized by many, but one of the most elegant formalizations of propositional calculus is due to the mathematician Hilbert. So propositions are capital letters. There is only one operator, which is the implication operation. There is a special symbol F, which is called false, and two more symbols, which are open parenthesis and closed parenthesis. Now, well-formed formulae are governed by this kind of BNF rules. A well-formed formula can be a proposition or the symbol F, or WFF implies WFF. That is the only way a well-formed formula can be obtained. And since the inference rule is what produces new formula, there is only one inference rule here. A implies B, and if A is given, then we can write B. This is called the rewrite rule. And the rule is known as modus ponens. Now, this is a very important development in human intellectual history, because these these places in very sound pedestal the whole process of reasoning, scientific inquiry, engineering artifacts, and explaining their operations, and so on. The whole thinking process indeed is based on this kind of systematization. And uh, again, Hilbert, of course, is credited with formulation of propositional calculus, but this method of capturing reasoning based on symbols, axioms, well-formed formula, and chain of inferences goes back to Aristotle in the Western world and Nyaya, the Nyaya system in our Indian system. We believe that ancient civilizations like Egypt and China also had their own formal systems for reasoning, as one can see from work of Confucius, for example. So this particular method of reasoning is very fundamental to any kind of intellectual work. So the relevance of this discussion to explainability is that when a new formula is derived, which is also called a theorem, we should be able to trace its arrival from the axioms to the application of this modus ponens inference rule. So if we can trace all the inference rule applications and the starting axiom, then we say that we have been able to explain this arrival of the formula from the axioms. Okay, so this is the notion of explanation in uh, classical logic, which is very fundamental to explainability research. Now, here is an example of what happens in the Hilbert's axiomatic system. So in Hilbert's axiomatic system, there are only three axioms, A1, A2, and A3, which you can see take this form: A implies B implies B A, and A implies B implies C implies A implies B implies A implies C. Third axiom is A implies F implies F implies F. So these axioms are the starting structures in Hilbert's propositional calculus. Now, now all these A's and B's are actually placeholders, which can be instantiated with constants, formulae, as well as longer expressions. So to see the power of these axioms and inference rules, Here is a proof of the tautology P implies P. So P implies P, we know, is a tautology. How do we say that this is a tautology? Now, the tautology's definition is that it should be coming from the axioms and application of inference rule. Nothing external is allowed. So the explanation for tautology, which is a self-evident expression, the explanation is that it should have a proof sequence. And indeed so, if we start with P implies P, and this is an axiom number one, and then P implies P, this is axiom number one again with a different instantiation. Then we have this structure, which is axiom number two. Now we apply modus ponens rules. So the second line is applied on the third line. We obtain the structure in the fourth line, and on the fourth line, if we apply modus ponens again and again, we will be able to obtain the formula P implies P. So P implies P is a tautology, and the explanation, okay, I repeat this point, the explanation is this whole sequence of structures which came from the axiom and inference rules. Okay, so this is a very different flavor of explainability which comes from classical logic, which today's machine learning is trying to emulate and go towards after settling all the concerns with respect to correlation. Now, I take another example which can be solved by using predicate calculus. So these such examples are like puzzles, and they also appear, for example, in competitive examinations. Here is a problem statement. A, B, and C belong to the Alpine Club. Every member in the club is either a mountain climber or a skier or both. A likes whatever B dislikes and dislikes whatever B likes. A likes rain and snow. No mountain climber likes rain, and every skier likes snow. So these facts and rules are given to us. No mountain climber likes rain is a rule. A belongs to the Alpine Club is a fact. So now the question based on this passage is there a member who is a mountain climber and not a skier? So we know there is a lot of work these days on machine comprehension. Machine comprehension is a hot area in natural language processing. Now, if this passage is given, and if this question is given, the answer will come out to be B. Okay, what is the reason? Because A, B, and C, all of them belong to the Alpine Club. Now, A likes whatever B dislikes and dislikes whatever B likes. Now, A likes rain and snow. A likes both rain and snow. Therefore, B cannot like rain and snow. And no mountain climber likes rain, and every skier likes snow. If B doesn't like snow, B cannot be a skier. And if B cannot be a skier, B must be a mountain climber, because anybody who belongs to the club is either a mountain climber or a skier or both. So this is the simple reasoning which goes there. Now, an interesting fact. If you try GPT-2, GPT-3, those kind of systems, or T5, which are deep learning based uh, uh, language models, and which rely on sentence completion, these are masked models. Okay, so if you give these paragraph, and if you give this question, T5 or GPT-3, GPT-2, because of their huge power obtained from huge amount of data and very large number of parameters. GPT-3, for example, has trillions of parameters, are able to answer questions like this. Okay, I myself haven't tried this, but some of you who are using GPTs do try this. And this is a very famous puzzle from a celebrated book called Theory of Computation by Zohar Manna. Now, it is possible to obtain answers to questions like this. But the point is that you cannot ask back T5 or GPT-3 or 2 as to why the answer is so. Okay, I produced an explanation. I say that A likes rain and snow, so therefore B cannot like rain and snow. And since B doesn't like snow, B cannot be a skier. Therefore, the only possibility left for B is that B must be a mountain climber. This is an explanation. Okay, so this cannot be obtained from GPT-3 to or 2 or T5. We cannot obtain. Okay, but we would like to obtain, and that requires research, which we'll see there has been some progress towards. But the classical logic, the predicate calculus based system can explain. Okay, so we have this detailed framework by which the natural language sentences can be converted to propositions and predicates like member A, that means A is a member of the Alpine Club. Then if X is a member of the club, then he or she must be a mountain climber or a skier. Every skier likes snow. No mountain climber likes rain. So there are predicate calculus formulations of this knowledge which is contained in the natural language paragraph. And not only that, from these predicate calculus expressions and by applying the method of resolution refutation, we turn the question into a negation of a statement. Okay, we first say that there is no such member who is a mountain climber and not a skier. So this is proof by contradiction or resolution refutation. So we are able to produce a tree. Okay, this is the resolution refutation tree. This is a property, the inversion of computer science tree, where the root has gone down and the tree has developed upwards, as happens in natural tree, but reverse of what happens in computer science trees. And since this null has arrived, we say that there is a contradiction in the system. It cannot be the case that there is no member who is a mountain climber and not a skier. Okay, we started with that proposition. And when we go through this tree, we are able to explain why the system arrived at this conclusion. This whole tree is the explanation tree. Okay, and that is very systematically obtained, very elegant uh, and very well established framework in classical logic. Classical logic, the decisions and inferences can be explained automatically because of the way the inferencing is done. All right. So now proceeding further, we do see that this kind of explanation trees used to be constructed in the early days of AI. For example, there was this mycin system, which was an assistant for diagnostics for doctors. And it had rules like this. If strain of organism is gram-net and morphology of the organism is rod, and aerobicity of org is aerobic. So these are medical terms. Then there is strongly suggestive evidence that the class of the organism is Enterobacteriaceae. Again, medical terms. And such rules constituted the mycin system. And when the mycins was queried on why a particular diagnosis has been made, the rule activations as above are shown. Okay, it shows you the complete chain of the rule activations, and that uh, constitutes the explanation of the decision. Modern days machine learning systems, okay, support vector machine, perceptron, these you can trace to an extent, okay, to the values of the parameters by which some explanation can be obtained. But deep neural networks of the scale of GPT-3 or T5 are completely unscrutable. It is impossible to give this kind of chain of facts because of which the decision has been taken. And that is where there is so much of intense investigation into how explanation can be obtained. But what is our model? What is our goal? And what is our ideal for explanation research? The ideal is this kind of structure which came from classical logic. And this, let us remember, is about 2000 years old. Now, this explanation tree is maintained by mycin, and anytime you query mycin about decision, this explanation tree is produced, which is more or less of the form of a tree. Okay, so now we'll move to explainability in the context of ML, which we will see is primarily a sensitivity analysis. But at this point, let me take a pause and ask if I have been audible and the slides have been visible so far.
So slides have been visible, no problem. There was minor glitches for about few seconds, but otherwise it's okay.
Otherwise, the sound is fine. Okay. Yeah. And do you see any question on the chat box or any question by anybody at this point?
Well, not yet, sir.
Not yet. Okay. So let me proceed. Explainability in the context of ML. So by now you are possibly convinced that this area needs attention, mainly because explanation is critical for any decision making. Without that, we cannot build trust. Ethics cannot be ensured. Transparency is not ensured. Okay, rigor and belief in the system is not possible without explanation. And fortunately for us, there is an ideal which we can strive towards for explainability, which came from classical logic. And in our Indian system, the Nyaya framework. Now, principal idea in explainability for machine learning is sensitivity. Okay, it establishes a correlation of decision with input parts and features. Uh, we again note that sensitivity analysis is not same as causality analysis. A scientist would want deeper insight, not just co-occurrence. Okay, the co-occurrence is observed, but why do they co-occur? Who causes what? Amongst the two factors which are co-occurring, which is the cause, which is the effect? Those are fundamental questions which need to be answered. Now, in terms of explainability, machine learning models fall in a spectrum. So to the left of us, we see a decision tree and also a linear separator. So these are interpretable models. So if I look at the decision tree here, I hope you can see it. TR production rate, uh, TR production rate, which is reduced. And then if it is normal, then we go to the decision about astigmatism. If there is astigmatism, then we investigate age, and then uh, we have come to the decision. Then again, we ask, is it not presbyopic or is it presbyopic? Then the decision is soft or none. And here there is a decision which is hard, and none. So these from medical domain, and there are technical terms, all of which I don't understand. But this illustrates the decision-making process where a question is asked on one of the factors, and from that factor we move to the second factor, and from there to the third, and so on, and we are able to produce a decision tree. And the explanation for the decision is right in front of us. The decision tree itself is the explanation. If we go into linear models of separation, linear regression, for example, then again we are able to uh, explain our decision, because these positive and negative classes are separated, and we can say these features place the decision on one side of the decision boundary, and other features place the decision on the other side of the decision boundary. Okay, this, by the way, forms the foundation for an important explanation algorithm, explainability algorithm, which is LIME. So let us remember this notion of decision boundary being linear. Okay, not a complex decision boundary, a linear decision boundary, and positive and negative points falling on either side of the decision boundary. Now, linear decision separation region is important. Okay, this actually helps us explain decisions. Okay, if we have a complex decision boundary, okay, which is the case for extremely large neural networks, the more complex the decision boundary, less explainable is the decision mechanism. Okay, I'll just repeat this point. More complex the decision boundary, less explainable is the decision mechanism. So on the interpretable model side, we have decision trees and we have linear separators. They're eminently explainable decision framework. On the other hand, the black boxes, which are not explainable or very minimally explainable, are the neural network based systems. So a simple feed-forward neural network is still explainable to an extent, because you can find out the sensitivity of the network to the input regions. On the other hand, there are neural networks which are much more complex. I mentioned these GPT series, T5, XLM, and so on, the language model, which are really inscrutable. Now, there is an interesting trade-off. The interpretable models have high explainability, but they have low accuracy and low robustness. I see a hello, sir. Is there some question or comment? I see a hello, sir, on the screen. Any problem with the reception? Can we get it by image classification? Okay, I'll come to this question a little later. Okay, you keep your question on the chat box. I'll come to it. So there is this interesting trade-off. High explainability often goes with low accuracy and low robustness. Low explainability leads to high accuracy and highly robust systems. So low accuracy can be explained because decision tree linearly separable models, they are often high precision but low recall systems. Okay, so if we have low recall, high precision, then the F score will be moderate. Okay, on the other hand, these low explainability systems push the accuracy level up by covering more data instances. Recall is typically higher there, and robustness is also high because these systems are more flexible. For example, if I work with word embeddings and not words, then we know that words which are close to each other, their embeddings also can be close to each other, and that can solve the data sparsity problem. Okay, so a system which works with word embedding suffers less from data sparsity than a system which works with only words. Okay, and there is this interesting fact that we are going from a discrete representation space to continuous representation space, which leads to higher robustness. Okay, so there are these two classes. There are these two classes of explainability neural network models. And decision trees actually are nodes where a question is asked. Okay, is there astigmatism, for example? The answer is yes or no. And depending on yes, I take a left branch. And if it is no, then I take the right branch. So this is how the decision tree operates. Now, this point about neural networks being unexplainable, inscrutable, is seen from such examples. This is a representative example. We constructed these for our multitask, dialogue, act, and emotion classification. So this network is not so terribly unexplainable. Okay, here you see the first compartment has the first block is three compartments: video signal, text signal, and the audio signal. And the intermediate block establishes correspondences between these signals through the attention network. And the final block gives the classification through softmax computation. So this neural network is still explainable because it has only three blocks, and each of these blocks do not have too many layers. But for extremely large neural networks, there can be layers and layers of neurons, and they are completely inexplainable. Now, the reason why deep learning models are inscrutable, so inscrutable, are because they are aimed to be end-to-end, both forward and backward. Okay, so the reason I mentioned backward is because there is a loss function whose value is minimized. We have to optimize an objective function. That happens by error backpropagation. Now, end-to-end deep neural network-based systems, there is only one technique to train the neural network. Whatever with the architecture, RNN, feedforward, LSTM, CNN, take any neural network architecture, there is only a single technique to train it. That is through backpropagation, okay, which is again essentially a gradient descent approach. And the objective function which is optimized is at the outermost layer. We minimize the loss at the outermost layer. Now, this raises a question about layered processing, one of whose best example is natural language processing, where we do morphological breaking of words, then grammatical categories assigned for part of speech tagging. Chunking is small phrase identification. Parsing produces a deep tree. Semantics, discourse, and co-reference, they deal with large passages, larger volumes of text. Now, is it that possible that only one loss function and one rule, which is backpropagation, can really optimize or can really make correct decisions for each of these stages? Okay, so there are questions being asked about whether NLP is really machine learning amenable. Okay, so machine learning consists of all these deep neural networks, support vector machine, perceptron, and so on. Is there more to natural language processing than just data and machine learning? The answer is indeed yes, because each of these uh, stages, take for example discourse, there is so much depth to discourse processing that this only one loss function and one rule, which is backpropagation, doesn't seem to be able to uh, tackle the demands of a complex problem like discourse. And that is what needs more and more investigation. There are indications that we need both rules and deep neural networks to tackle such problems. Now, here is an example of the correlation that is established within neural networks. So that is through the mechanism of attention. By the way, attention is a great contribution coming from a deep neural network, which has a data-driven, machine learning-based capturing of correlation between decision and the input. Okay, so there is already a explanation framework based on attention. If we can track the attention, we are able to track explainability. Now, Peter slept early is an English sentence, and A's and B's are activations in a by LSTM or by GRM, where there is forward propagation of activation and there is backward propagation of activation, because the sentence is read left to right as well as right to left. So when we do so, we have these context vector created out of these word embeddings of Peter slept early, beginning of sentence, end of sentence. And if it is a machine translation system, then the output will be Peter jaldi soya. So here, Peter to Peter, there is a correspondence. Slept to soya, early to jaldi. So this is known as the word alignment problem, which is again a very important development in statistical machine translation, data-driven statistical machine translation. Now, this attention of Peter to Peter, jaldi to early, and soya to slept, this attention is created inside the deep neural network because of the training data through the attention weights. Okay, these large neural networks are already doing. And the feed-forward network gets trained for attention weights from the data. Now, the same objective function for all weights is optimized for encoder, attention, decoder. Okay, this is something to know. If we take a transformer network, there are many blocks of this form: feed forward, multi-head attention, and then feed forward, multi-head attention again. So these blocks constitute a transformer network which is sufficiently complex. But let us note that all these blocks get optimized by the same objective function. Okay, an objective function which is there at the outermost layer. This is a supervised learning framework. And when we do so, we get the attention weights, and this we can exploit for explaining the decision. So this network, once again, which does dialogue act classification and emotion classification at the same time. Now, if we do not ensure explainability in neural networks, there can be mishaps. So here is an example where Google Photos uh, wrongly labels humans as gorilla. Okay, so this is a wrong classification, wrong image labeling. And here is an example where a New Zealand passport software rejects an application by mistakenly detecting the eyes as closed. The eyes are actually small here, they are not closed, but the passport processing software rejected this application, which is again not desirable. And sometimes it can be dangerous in case of health and judicial systems. So now black box mishaps can also happen in natural language processing. For example, this is an emotion analysis situation. The conversation with Justin was exciting. The model predicted that the emotion is joy. The conversation with Malik was exciting. Here, the emotion analysis system predicted the emotion as anger. Okay, even though the the sentences are almost identical except for the change in name. So this is from a work in 2018, which evaluated 2015 to 215 sentiment emotion analysis systems, and there was this equity evaluation corpus EEC, which is a benchmark data, and 200 of these 215 sentiment emotion analysis systems suffered from such biases. And if one uh, tracks as to what is going wrong, we see that the system is giving importance to names, okay, instead of giving importance to really the triggering words. The word exciting should be the focus word based on which the emotion should be identified, and it gave importance to the names, and therefore the emotion got differently labeled. So this was wrong, and this was a wrong operation on the part of the machine learning model, and this needs to be corrected, before which we need to explain the behavior of the model. So this gives the motivation for explainability, especially in the context of machine learning. The motivations are increasing of trust, causality should be revealed, identifying and mitigating biases, and we should extract knowledge from the trained neural network model. The extracted knowledge is in the form of a set of rules. Now we look at some of the techniques for explainability for machine learning. So we see mainly four paradigms: the black box model explanation, black box outcome explanation, black box inspection uh, uh, framework, and the transparent box design. So here is an illustration for each of these paradigms. In black box model explanation, what happens is that we get the explanation through a surrogate. So the black box learning has happened. The black box predictor is a neural network, and this is mirrored or shadowed by a predictor which is more explainable. So we simulate the neural network by decision tree, and that decision tree serves to explain the working of the model. This is black box model explanation. Outcome explanation is that we find out from the output which pixels, this is a cat versus dog recognition situation, which pixels are becoming activated, okay? And this is the outcome, this outcome, and that outcome serves this segmented outcomes, okay? Focused outcomes serve as the explanation. And if we go to sensitivity analysis, which is very similar to the outcome-based explanation, except that in outcomes we identify which pixels are contributing to this decision. In sensitivity analysis, we inspect the weights in the neural network, okay, parameters in the neural network. And in the transparent box design, right from the beginning, instead of a neural network, we have a rule-based system, okay? So the rule-based system produces the decision-making system, and this itself also provides the explanation also. So if we look at all these paradigms, the two major divisions are the outcome sensitivity and the parameter sensitivity. And the shadowing mechanism is also quite prevalent, but that's a much more difficult uh, difficult proposition to obtain, because you cannot really shadow a very complex neural network with a decision tree. Decision trees are limited in their power of expression. A neural network which has trillions of parameters will possibly require million decision trees, which is very difficult to obtain and maintain. Decision trees are obtained by what is called entropy minimization, and it's a greedy strategy. Now, some techniques which have become quite famous, I mentioned three of them. The first is locally interpretable model agnostic explanation. This is also known as LIME. And this technique has somehow stayed in the area, and people go back to the LIME principles whenever they design a new explanatory framework. So it works as follows. Suppose we have these features: sneezing, uh, weight loss, headache, no fatigue, and there is also an age value coming as a parameter. And from that, suppose we decide the person has flu, then Lyme can identify which are the contributing factors. Sneezing and headache are the contributing factors. No fatigue has no role to play in this decision making. So this is based on a methodology called perturbation, and it works as follows. Uh, the decision boundary can be very complex, but Lyme focuses attention on a local part of the decision separation region and draws a separator separating positive points from negative points. Okay, and while this separator is placed, it identifies the contributing features which can make local separation of points possible. Okay, so from the local behavior, we try to guess which are the actual contributing factors. And here the foundation is linear separability. So this is how Lyme works. Now this is based on perturbation. Here is an example which is given. This is the picture of a frog, and the decision is that this animal or the picture is a frog, and when we perturb, we switch on and switch off features, then we see that this peculiar location of the eyes as well as the configuration of the mouth contributes to the decision of frog. The frogness lies in the peculiar position of the eyes and the configuration of the mouth. Okay, so this the Lyme system can identify. So there are lots of code, lot of code base available for Lyme. There are demos also, which I've given the URL for. The next technique is called layer-wise relevance propagation, or LRP. LRP is being used quite extensively in recent times because the motivation comes from backpropagation. So in LRP, without going into a lot of detail, I say that the relevance is backpropagated. Okay, relevance is backpropagated. There is a forward pass where we obtain the output decision from the input. And when we backpropagate the relevance, we get something like a heat map. And that shows the segments in the input region which are contributing to the decision. Okay. By the way, a lot of explainability is founded on image related research. Okay, getting decisions on image and their properties, and there the words like segment, etc., makes a lot of sense. But when it comes to NLP, it is the words which need to be focused on, and therefore segment for NLP actually means words. So relevance backpropagation happens, and there is a kind of invariance condition which says that the total relevance at a particular layer should be preserved. Okay, so this is an important foundation for this technique, and based on this, one can form recurrence relations, and the relevance is backpropagated to identify the sensitive regions in the input. So there is a interesting connection between LRP and convolutional neural network. The convolutional neural network actually uses filters, and for NLP, these filters actually amount to n-grams, bigrams, trigrams, quadrigrams, etc. And LRP can identify which bigrams or trigrams are important for the decision making. This happens by investigating these layers of filters, and also the max pooling, the ReLU. CNN as an architecture is quite systematized. Almost all CNNs have this very regular architecture. Okay, there is a filter, there is a max pool layer, pooling layer, and there is this ReLU, and then finally a feed-forward network. So one can focus on these different blocks, which are almost universally appears in all CNNs, and then LRP is a very nice explainability framework for CNN-based systems. So through LRP, for example, one can identify the contributing features for this decision on a sentence like this. I am going to have to be the first to negatively review this product. So this is a complexly expressed opinion. The opinion here is negative. So I am going to have to be the first to negatively review the product. Here the main sensitive word is negatively. Okay, other words are not really very relevant. So this is identified by LRP. Now, then the third approach is called the integrated gradient approach. This is also quite recent, but was uh, invented in 2017. And there are two axioms in IG framework. Sensitivity: if the model and the baseline differ in exactly one feature, that feature should get the high attribution. This is common sense, but this is interestingly exploited in the IG algorithm. Implementation invariance: attributions are identical for two functionally equivalent networks. So if you have two neural networks of different architecture, initialized differently, different training algorithm, uh, they would be invariant with respect to explanation. Okay, so these are the cornerstones of the integrated gradient based technique. So here, um, this is the main formula in integrated gradient based approach. This is also fundamentally a sensitivity analysis. You can see the approach is based on a gradient of the decision function with respect to the input, and this gradient shows the sensitivity of the input segment for the decision. Now, based on integrated gradient, we can give explanation for these kind of predictions. How many townships have population above 50? So this is a question classification example, and this question uh, is of type numeric. Why is it numeric? That is because of the presence of the phrase how many. Then if we look at this question categorization, which is a string, which film was before the audacity of democracy? So this is of type string because of the phrase which film. This question is of type date time. This is because of the presence of the keyword year. So IG, integrated gradient, can discover both positive contributions and negative contributions. But all of these are really, I would say, in their infancy when it comes to tackling a very powerful neural network. Now, turning an explanation into technique, this is an important research. We do see these days explanation being integrated into the prediction process. Okay, the loss function has a component which is minimizing the loss of the observation with respect to the target behavior. But there is also an explanation component which is added to the classical loss component so that the prediction becomes better. And the intuition is that if an entity can explain its behavior, it can predict also well. Okay. So now, for example, we mentioned the Newton's third law of motion. Now, the horse actually is pulling a cart and it is moving forward. The many times there is a confusion in the mind of a first-time physicist that if the horse is pulling the cart and cart is also pulling the horse, how come the whole assembly is moving forward together? So here we have to resort to Newton's first law of motion, which says that for any system to have acceleration, it must have an external impressed force. And here the external force comes from the ground as the horse pushes on the ground. Okay, so that constitutes a proper explanation. Now, whether an assembly will move forward or not, that prediction is facilitated by this kind of explanation. So, techniques have uh, been have benefited from the notion of explanation. So we have done quite a lot of research in sarcasm detection, and we have traced that the explanation for sarcasm is incongruity. And the moment we realized that, it facilitated our design of algorithms for sarcasm detection. So if we look at this picture here, wow, well done. This is a positive text. But look at the facial expression, look at the body language, look at the configuration of the hand. All of these are pointing to negativity. Okay, so this combined occurrence of positive text and negative body expression indicates sarcasm. So when we understood that the explanation for sarcasm lies in incongruity, we could design an algorithm which could tackle a complex phenomenon like sarcasm. So indeed, we tackle sarcasm detection using semantic incongruity. And here we of course exploited all the regular features of sentiment analysis and text classification, like unigrams, capitalization, implicit phrases, explicit phrases. We don't have time to go into those details. We made use of standard data set for evaluating our sarcasm detection system. And we also made use of word embedding based similarity. After we have done all that, uh, then we could uh, design a system which is better than the state of the art for different kinds of embeddings and different kinds of baseline. So this was possible. This was possible, I repeat, because of the capturing of incongruity. And how was incongruity captured? Incongruity was captured by computing cosine similarity for sentences like this. A man needs a woman like a fish needs bicycle. This came from the tweet. And the cosine similarity between fish and bicycle is very low, whereas cosine similarity between man and woman is high. I'm talking about the word embeddings. And the preposition is like, which demands that to the left of it and to the right of it, the behavior of the text should be same. If that behavior is not same, then it is an incongruity case. So we exploited this idea and introduced a feature based on word embedding similarity. This was motivated by incongruity, which is an explanation for sarcasm. And our results were better than what was the state of the art. And this was reported, of course. Finally, in the last part of the talk, I go into an interesting research that we have undertaken. And this is the exploitation of gaze behavior. Now, it is very difficult to get gaze data. Okay, for it is very difficult to get gold standard data for explanation. If you have to create an automated explanation system, okay, then we have to evaluate that explanation system. That requires gold standard data. And getting gold standard data for explanation is very, very difficult. When an annotator is annotating the data, it is additional work for the annotator to say, to explain why this annotation is being done. Okay, that's difficult. So we'll see how this problem can be solved little later. But we understood the power of eye tracking for many different problems like sentiment analysis, um, text classification, and I show you the example of automatic essay grading. Now, automatic essay grading is a problem of scale. There are huge number of students all over the world, but the number of teachers are uh, far fewer than what is really required. So we attempted to create a system which will solve this problem of scale. And we wanted to create a system which will make use of the input essays different features and classify the essay as good or bad. So here we made use of also an additional feature, which is the eye tracking behavior. So we have seen that teachers, when they read a good essay, the movement of the eye is very smooth. It almost effortlessly moves from word to word, forward, sentence to sentence. There is not much back and forth movement. But if an essay is badly written, then there is a lot of back and forth movement, and that indicates the cognitive complexity and the cognitive burden which is on the teacher. So here, the dark regions are the regions where the eye has rested for a longer duration. The lighter blue regions are where the eye is spending less time. And this is the eye tracking behavior for one of the essays. The darker the blue, the larger is the dwell time. So the dwell time example for a good essay, notice the lack of dark blue parts. So if an essay is well written, then we do see that the eye doesn't spend too much time. It doesn't uh, get an obstacle, okay, on in its processing of the text. Whereas for badly written essays, we do see lots of dark regions. So this is a behavior which we obtain from our cognitive science lab in our, which is a part of our NLP lab. And there are also saccades, which is regress and progress, and we do see lots of such behavior for badly written essays. So we made use of this particular property of the text and the reader combination. So it was a combination of reader and the text. So we captured the fixation, saccade, all these as features. And the text quality rating had these three decisions: organization, how well structured is the essay, how much sense the text makes, and cohesion, how well connected the text is. So the quality of an essay is a function of organization, coherence, and cohesion. So we had a data set whose details we don't have time to go into. And there was different genres of text like history, politics, law, education. This, by the way, is part of the PhD work that a student did with me, Dr. Sandeep Matthias. Now, the annotators were qualified to annotate this data. There were text-based features like length, stylistic feature, word embedding features, and so on. In addition to that, we also made use of gaze-based features. So the experimental setup made use of a combination of all features. I come directly to the results, which showed that on all these, organization, coherence, cohesion, quality, the text plus gaze gave better numbers compared to only text or only gaze. And in particular, you can see the difference in value. The difference in value is much more pronounced for the property of cohesion. In case of cohesion, if you have only text, then the value is 0.120. If we make use of text and gaze both, then it is 0.451. The difference is much more for cohesion. Why so? Cohesion is a property which requires back and forth movement over the text. And if the cohesion is bad, there is frequent regression and progression on the text. Okay, and that is why this difference is much more pronounced when we make use of text and gaze. So this was observed quite comprehensively for all kinds of essays. And when we did the ablation study, we found that for organization, the fixation was an important feature. Coherence, uh, for cohesion, the regression was the important feature. For coherence, interest area, organization also interest area, and quality interest area, that is the time I spent on a particular word or a phrase, that became the important feature, which was consistent with the intuition. And finally, this solving the bottleneck for explainability, which is the lack of gold standard data. I'll have to speed up on this part. So here we understood that it is not easy to get gold standard data. So then we found a hypothesis that those text segments where the eye rests for a long duration are the clues for making predictions. Okay, so those are the features which contribute to decision making, and you can capture it from the eye of the annotator. The annotator doesn't have to make an extra effort to identify those features. Okay, so that we did, and our approach was to really take data level and the eye tracking signal. So if I take this sentence, this movie is very good, then the eye actually rests on good and very good, spends time on this, and that becomes our explanatory signal. So this is an example from adverse drug reaction to it: migraines, mood swings, muscle cramps, spasms, heavy bleeding, cramping, and more. I hate this pill. So this is an opinion about a pill which the person purchased for his ailment, and saw that these are the um, side effects. Okay, heavy bleeding, spasm, muscle cramp, and so on. And in this opinionated text sentiment, we could see that the eye rests for quite some time on these side effects, and they are the explanations for this negative sentiment. So this is interesting, and we contributed quite a lot of data. All this CFILT quality, CFILT scan path, CFILT sarcasm, CFILT sentiment, all these data are contributed by us for eye tracking research, which makes use of cognitive signals for NLP. So the evaluation data set was obtained from eye tracking, and this we call the silver standard data. As is usual, we trained a BART language model for uh, evaluating the explanatory capability of the techniques. And then we found that this eye tracking data is quite consistent with the explanations which come from sentiment bearing word. So this was our baseline. We latched onto sentiment bearing words in the sentence and said that these are the contributors to positive or negative sentiment. And this had good correlation with eye tracking. And we did another study that we could organize some amount of gold standard data. And this shows the uh, the progression of F score when we include more and more words into the explanation. And the explanation really becomes uh, pointless or completely shallow as we include more and more words. The words which actually correspond to decision making, they get they get identified really well by eye tracking. Okay, so these are some of our findings. I would like to now summarize my talk. So summarize this part, which is the eye tracking based system. So the annotated data was obtained for sentiment analysis, but we also obtained silver standard data by tracking the eye of the annotators. Now the summary of the whole talk here. So I described the contribution of classical logic to explainability. That is our idea. We have to reach there. Classification decisions in machine learning models have to be explained in critical areas like health, judicial system, and so on. But here, the explanation mainly consists of sensitivity of features. So we discussed perturbation-based, sensitivity-based, and relevance propagation-based methods. We also could see that if we understand the phenomenon well, then the technique is also designed more effectively. An example that we ourselves have been party to is the sarcasm detection. The moment we detected the explanation for sarcasm lies in incongruity, the algorithm design became more effective. We can also break a problem into its parts, like technique design and explainability. That was corroborated by the work on automatic essay grading. And we are trying to solve the evaluation data bottleneck by using cognitive signals, creating what is called the silver standard data. So some of the conclusions are the following. Explaining the working of machine learning model is a critical necessity that can only build trust in machine learning models. And some domains are really sensitive to explanations: health, judiciary, aircraft navigation, and so on. I mean, all of which we are working on information extraction problem. Shadowing a deep neural network is an important explanation methodology. It is very attractive. The only problem is that the uh, white box models are much less powerful than the black box models. Uh, Evaluating the explanation systems is a challenge due to lack of gold standard data. Cognitive natural language processing can really come to help here. And we really have to move to causality analysis. That is a very critical necessity. We still do not give causes of decisions. So everything I said is linked uh, from my homepage in the form of publications. And we have made a lot of tools and resources available through our lab, the CFIELD, Center for Indian Language Technology in IIT Bombay. And I would like to thank you for your attention. Thank you very much.